It's already. So the last time we had this, now I'll formally say we had this. So last time we had this Euler's Totient function. I just turn off the video here. Okay. We looked at Euler's Totient function. Yeah. So what is this? Well, this is just a function which tries to ask an important question. It's denoted by phi of n, means the phi is the name, and n means on input n, what does it do? So can anybody define it? Factors of n, no, that's a different function. Yeah, so you just the name maybe. So anyone else? So what was that one thing that you were interested in last time? Given a number n, yeah. Yes, right. And it's a sort of like complement of factors, sort of, not exactly, but yeah, yes. So this is basically, let's write it again, no harm, right? Number of numbers coprime to n and less than n. And then let's not go back into the history of how it came. Yeah, one doesn't need to remember all that. One needs to just know that they know and they can build it. Number of numbers coprime to n and less than equal to n, right? And we found a formula for this. So please, someone tell me the formula if you remember, or if you have thought about it in some other way. Or for 2, if you want me to do something more specific, you can tell me n equal to a specific thing and say. Right? So we had derived a formula, right? In a very simple, that's not usually how it is done. Yeah. But in a very simple way, well, that's a standard thing. Well, if you do inclusion and exclusion principle in chapter, it will be there, but not in a number 3 book. Usually they won't prove it like that. They'll prove it in a much better way, elegant way maybe. So, well, yes, exactly. And in the case when there are, let's say, k prime factors, so now we can go into k prime factors. Okay. So not to be afraid with these expressions, right? Because this is what every number looks like, right? This thing times, yeah. So I guess we're just recalling a few things from the last class. We did say a few things earlier about what we will do next time, but right now we're just recalling these things. This formula, and so this very elegant formula, right? That tells us, I mean, just see, the formula here does not just have a computational use. It is not just a computational advantage that you get. You do get that, but the formula tells you something, or rather many qualitative facts about this number, about this function, right? That is the point. So okay, has anybody, like, what does this formula tell you? Has anybody thought about it? Can you put it in words? What does knowing this formula, how does it help you? When I thought about it? Okay. No problem. So that is all right. Then let me ask a question. Through that, maybe you can, yeah. Okay. So if yeah, but now you guys know the formula, so it's pretty straightforward. But so then let's do the straightforward thing, no problem, right? if phi of, oh no, so let me just say this. Yeah, sorry. Find phi of 42 without using the formula. Let's see. Let's see how you. So just want to know how you would find out phi of 42. So you can try to connect this with the fact that phi of 7 is 6, which we all know, and phi of 6 is 4. No, it's must be much smaller. 2, and we all know that this is very simple. Yes. Oh, sorry. Phi of 6 is no. So certainly not, because 1 and 5 are there. Yeah. Phi of 6 is 2. Yeah. And so if you calculate phi of 42, you will see that it is 12. It's not hard to calculate. You can also apply the formula and check. It's 12. And then you see what the point that I'm trying to make. And if you have tried, I hope you have tried more examples. So what is the pattern? What is the connection? Right? I mean, so this 12 and this 6 and 2, right? So, I mean, it is clear. So the pattern that is there is simply, yes, that's right, right? So phi of the product of two numbers, that's what it seems like so far. Phi of the product of two numbers is equal to the product of the phi of the two numbers, right? So the product and the phi, you can exchange those words, phrases. They commute. Is commute meaning that, like the commutator of a fan. I don't know how that word comes, but they commute. You can, yeah, exchange them. So you could first compute the phi and then compute the product, or you can first compute the product and then compute the phi. They remain. This is a deep thing. It's a, if you think about it, it seems something very good, right? It seems something very good, at least. That's what I'm trying to say, right? So is this thing always true? That is the first. Before we go into discussion, is this, because this is a short question, is this always true? So is phi of n1, and all you need to just do is take a lot of examples and check, right? Is, so this is just a question, okay? Is this, and this exploration that we are doing for this function, this particular exploration will apply to number of different functions. Okay, later though you don't have to do this exploration again. The same features apply to many of them. So, but first, simple question is this always true? If it is not, then we have to stop, or have to then we have to modify things or see. Yeah. Just take some examples and take different kinds of examples. For 12. Okay. Right. So how did you do 4 into 3? Okay. Right. Right. How about take some other number? Maybe how about if I take 16? 16, if you break up 16 into 2, then does it work? Maybe break it up into 4 and 4. Yeah, so what factorization did you take? 6 into 6. And so it, I hope that you get, I don't know actually, wait 1 minute. Yeah, do you get, so what do you get on both the sides? Well, it's easy, we can just check. 6 is 2, so this is this side we get 4, right? So no, intuition was wrong. And so what is phi of 36? You could try to calculate it by, yeah, but we don't know. But just calculate and tell me using the formula or whatever. You're getting 12. Others have checked. Just put it in this formula, 12, right? So let's just do this in the sense 36, and then we just apply the formula. So we get 1 by 3 and we get 1 minus 1 by 2, and you can just check. So it's like this is the P1 and this is the P2, and these are the only two factors, right? 3 and 2. You get 12. So certainly not true. Then you're getting it is true. But when you do 6 into 6, then you're getting it is, then it's not true. So then what is the explanation? Must be coprime. So that's the guess, right? And now this is, you should try to explore this further and establish this fact. Okay. You should try to explore this further and establish this fact. So what we have basically learned, and everything is there on the board itself, that if you take two coprime numbers, then it will certainly be true. Okay. So if n1 and n2 so n1 and n2, they are coprime, then this is multiplicative, right? It's not bad, right? Not bad. So why do you think it is failing? Just think for some time. Why it is failing when they are not coprime? So some factors are overlapping, but then yes, exactly. So that thing, I mean, so yeah, so the first part is not a problem, and so that might, if you say, if you just think about the first part, then it should be multiplicative always, right? But so the point here is that when you take the second part, then the second part seems to be you seem to take it multiple times, right? If there is a common factor, right? So if n1 and n2 have a common factor, right? Let's just take one more example, then it will be clear. I'm just doing it here. So we take one more example. This time we take equal numbers, so you know. But if we take one more example, no, what should we take? 6, 3 and 12. Yeah, 3 and 12 is fine. But I want to take, yeah, 3 and 12 is fine, but take something a little which is not dividing also. So let's say 6 into 8, right? So you see, so when you calculate this, then you do 6 into 8, that is fine. But here you do 1 minus 2 and you do 1 minus 3, right? But when you break it up, right, and they have a GCD, means that they have a, and this is very important fact, that when two, I mean, this is a trivial fact, but it seems to be crucial somehow, that when two things have a GCD, then they have a common prime. And because, you know, primes are somehow have more specific properties. This thing, when you calculate, just doing it here down here, when you calculate this, then the 6 and 8, they are fine, right? They are just there. But here you see you do this and you do this 2. But then 2 is the common, is a common prime factor, right? And so you have to do this 2 for this also. Okay. And so that that changes the answer. So that will change the answer. I mean, that will always change the answer, right? So this is a if and only if thing. You see, it will have to change the answer. The answer cannot be same, right? Because 1 minus 1 by p1 cannot be 1, right? So it will change the answer on the other side. But then, do you guys see that we always have this? Can you explain why you always have this? Why phi of n1 times n2 is at least phi of n1 times phi of n2. It is already there in the explanation we have given. So that's why I'm asking, so you can think and see. Right. Mm-hmm. Yes. Yeah. The point is that the extra things that we're multiplying is in fact less than 1. Right. So if this pi is a common factor, is a common factor of n1 and n2, then you'll have an extra 1 minus p1 or extra 1 minus pi. But that will in fact reduce the product because it's less than 1. The small things, yeah, small things. But if you don't think, then suddenly we can get. So that's why you see these things I'm doing. You guys can just think about these things. So the point is to just sit with the pen and paper sometimes. Just keep everything away and just, yeah, whenever you feel like, just remove other things. Not even a book, just pen and paper, and just take some examples. See, so when you feel like, just go with it and do it, and do more of it when you want to do it. Then it's really, then you get some interesting things. Good. So so far it seems okay. Yeah. Now another interesting question is that interesting thing that comes to mind, which is usually like not I don't know, asked or I don't know, but it comes to mind is when phi of n divides n, because it seems to have factors, a lot of factors in common, but then, so what? Like, can it divide n? Can you give some examples, at least examples, or say something more? Because phi of n is less than n, that's clear. But when does it divide n is the question. Yeah, there are many interesting questions on phi of n. Yeah, I don't know most of them, but little I can think there are many interesting questions come. But that we will not explore, that we keep doing it. Later we will, you can think and ask. That's but this question is standard, I think, maybe a little standard, I don't know. Can you find at least one example? Yeah. Two is, yeah, two is there. Yeah. 12. So someone said 12, right? Aparna said 12. So yeah, in 12, so what is phi of 12? 4. Good. Okay. So so why did 12 work? Right? That is, it's 2 into 3, 4, 2 square into 3. Right? Does it also work for 6? Yes, it does. Okay. Any more examples in some general thing? And something is similar between 12 and 6, obviously, but doesn't work for 9. Yeah, it will certainly not, it will not work for 9, right? But yeah, we can note that. It's good to note that. So I mean, once I've written phi n dividing n, so we understand that that is the n and this is the phi n. So what is phi of 9? It's 6. Okay, doesn't divide. Good. It works for 18 also. That's that is what I was also just thinking. There is something going on, right? Does it only work for multiples of 6? Yeah, so let's no. Okay, yeah, so 18 is yeah, 18 is there. So I don't know. Yes, that is, yeah. So you have to think about this. I mean, that will be better. Yeah? That is a good. Sorry. $14. No, it doesn't work for 14, right? So sorry, just tell me for 18, what is it? What is the fee of 18? Just something, I don't know. 9, 6. Yeah, it's just 6, right? Yeah, exactly. Just this only. So it doesn't work for 14. So for 14, because for 14 also it is 6, right? Yeah, and it doesn't work, right? It works for 16. Yes. Okay. So what is phi of 16? It is 8, right? So it works for any power of 2. Okay, good. So it works for any power of 2, because so what is it for 2 to the power n? So it is half of it, right? So certainly works. So 6 is not the only, yeah. Can you find a number in which doesn't have 2 as a prime factor and it works? Because what I see common so far is there is 2 is a common factor. So if 2 is not a, I mean, common means if 2 is not a factor, if 2 is not a factor, then will it work? Okay, so what is the explanation? Which will always give you more than half. No, but then if you multiply several of these things which are more than half, the product can be less than half. Right? If it has many prime factors, so then it can become less. And that's a very interesting question. This is a very interesting question. What happens to phi of n by n as n goes to infinity for certain specific kind of numbers? Sorry, as n becomes very, very large, what happens to this ratio? So for certain kinds of numbers, this ratio goes to 1. And for certain, I mean, okay, maybe I just said, yeah, for certain kind of numbers, this ratio goes to 1, for example, prime numbers. And then there are some other interesting questions that one can think, but I'm not, because limits and so on, we have not yet so comfortable, so we're not doing that. But this thing, so, but but I think your claim is correct in the sense that 2 has to be there. Let's try to see, because we have already made this progress. So 2 has to. So for 5, so for doesn't work. Yeah, good. So 15, let's write it here only. So let me just erase this thing, or not erase this, put this here. Because this is the explorations, you see, because number theory is filled with these, obviously, number theory, so much work has been done that I don't think in this kind of number theory, there is any hope for you to do anything new now. But you see, if you keep doing this, it's not important to do anything new. I'm not saying like that, but a lot of things like additive number theory and a lot of things are there which are simple things which not many people care about, and they are simple in the sense that there is no known theory, and so people can come and just prove a small lemma and go. Anyone can do, in a sense. No, not much background is needed for a lot of things. Obviously, for multiplicative number theory, it is people are doing it since, yeah. So it's difficult to find. You then for that you need an expert who can actually give you some questions which are not well known, and yeah. So I'm not much. I don't know. Yeah, and easy. That is the thing. No, so the point that I was, yeah, so it doesn't work for 15, so I'm not writing it. It's fine. It doesn't work for 15. No, so the other thing which I wanted to say was, how about 30? Does it work for, no, so does it work for 30? Let's just see. I think it doesn't work, but let's just check. So 30 is it, so it doesn't work. Right. Sorry. Yes, it does have a 2. Yeah, but still it doesn't work. So the point is that just having a 2 is not a guarantee. Yeah, that's right. Um, right. So, but why I was saying that you should have a 2 at least. I mean, that's a necessary condition. It doesn't mean that having a 2 is, yeah. Why you should have a 2 is because, see, if you look at this number can also be written like this. Yeah. Alpha 1 minus 1, alpha 2 minus 1, and so on. And then we have alpha k minus 1, right? And then you have this p1 minus 1, p2 minus 1, and now you can see a little bit pk minus 1, right? So p1 minus 1, p2 minus 1, till pk minus 1. So one less than that factor. That is the thing. Now, what is n by phi n? What is it, right? So it is this thing, this p1 minus 1, p2 minus 1. Okay, I might be wrong in saying that 2 has to be there. I was just thinking. So p1, p2 till pk. I mean, if you divide everything, then this is what you get. No, so it's the opposite of this. Sorry. I mean, this will not never be an integer, right? It's less than 1. And it will be the opposite of it. Just dividing and canceling and so on will tell you. Yeah. Right. So you see what is happening, right? I mean, let's just assume that there are 3 prime factors. Let's for a moment just simplify it. Or let's just even take that there are 2 prime factors and then try to see. Yeah. So what are we getting from here, right? That see this p1 minus 1 guy, right? This has to divide the numerator, right? So if p1 is a prime, if p1 is a prime that is there in n, right? p1 is a prime that was there in n, prime divisor of n, then this p1 minus 1 has to divide p1 times p2. But it obviously has nothing to do with, it has no factors with p1, right? So we can say that this p1 minus 1 must divide p2 because p1 minus 1 and p1 are co-prime. There's no prime factors, obviously. So this p1 minus 1 must divide p2, right? What does this say? It is yeah. So if p no, but if p1 itself is 2, then it means that there are no other primes, right? In the sense, I mean, let us say that p1 is bigger than p2, right? So that we have already seen that 2 to the power n, it works, right? Always. Yeah, so that is correct. If p1 itself is 2, then it works. But this p1 minus 1, yeah, so p1 minus 1 must divide p2, which means that if p1 is a prime and p1 is not 2, if P1 is 2, then P2 is not there, everything is done, fine, everything is okay. Assume that P1 is not 2. Okay. Then I'm thinking that, what does it mean? It means that this P1 minus 1 has to divide P2, right? But what does it mean? Well, P1 minus 1 has 2 as a factor. P1 minus 1 is even, right? P1, yeah, yes, exactly. So that's what I was, yes, that's right. So then what does it mean? Yes, there is no other choice, right? I think that's a much better way to say it. So P1 minus 1 has to be equal to P2, or it has to, but assuming it's not 1, then this P1 minus 1 has to be a prime, and it has to be equal to P2. Yes, because the other case we have already done, so we should not think about that. So P1 minus 1 is a prime, and it must be equal to P2. But P1 minus 1 is even. And so this has to be 2. See, there is no other choice, right? So I have not done anything. It's just little nothing, right? And so what does it mean? It means that the second one has to be 2, and the first one has to be 3. If there are 2 prime factors. Yeah, if there are 2 prime factors. Right? And so we seem to have a complete, so I was thinking it's much more deep, but it's not, apparently, because this this thing just means that this has to be equal. Yeah. So basically nothing, then it's easy. So it has to be 3, and P2 has to be 2. The powers can be anything, and you see the powers can be anything. It doesn't matter, right? And the powers of P1 and P2 can be anything. So this happens. So we have a complete answer. I did not know this question before. I have probably never thought about this question before. Just to say something interesting, I just, or something different, just did it. But this kind of arguments are, and it's just interesting, are always present and interesting. And remember, and if you're doing like Olympiad maths or some entrance this thing exam, they don't care if you know some big theorems, and usually they will never ask question unless it's some big Olympiad, some national or international. Even there, they try to make their questions which don't involve theorems too much. Point is, you have to do simple analysis. This is too simple for that, but the point is, it is there. Or maybe for common entrance, it is fine. But that's not the point. Point is that we have shown that, and his point is that you should not rely on theorems too much and just do the analysis. Okay, theorems are come also from this analyzing these things. Okay, so the point is that it can be anything, like, so it seems like that, right? That this can be anything like this. And obviously the alpha 2 can be 0 as well, but the alpha 1 cannot be 0. Right? That already for 9 we checked, right? So also maybe you can write that alpha 1 cannot be 0, because 2 has to be there, that we have seen in the analysis also. Okay, so this is the first problem in that, and you will see many more problems as you get more. Yeah. Okay. All right, after yes. Oh, okay, sorry, yeah, so that was a, oh no, yes, so I skipped some things, I think. Yes, but I think it cannot have more than 2 primes, because I mean, let's say you write P3, and but we already saw that the P2 has to be 2, or did we see that? No, sorry. Yes, no, but the problem is that we assume that there is no third one. So okay, let's come there. Yeah, slightly incomplete to say, at least it might be correct, but incomplete in the sense. So it might also happen that, so if p1 minus 1 divides p2, yeah, I got too carried away. It implies that p2 is 2, p1 is 3, and then done, nothing else to do. But now the other thing is that if this divides p3, then what can we say? It has to divide, I mean, it has to, okay, so it need not, sorry, so that is also not true, right? It did not even divide any, no, so because this is not a prime. Yeah, this is not a prime, so it did not divide any one of them, but it may have one of them as the factors, right? So then, you see, right, p1 minus 1 is not a prime, so it doesn't have to divide one of 1 pi. I mean, it can divide the product. Yeah? But you see, there is a small thing here, right? That this is, so I mean, at least two of them are even, right? At least two of these are even. Do you guys agree? Yeah, because I mean, only one of them can be two, right? The other two are odd primes, and so they're, yeah. So this has maybe this, so this is even, and this is even. Then we have two twos, right? We have 2 square in the denominator, but 2 square is not there in the, it cannot be there in the numerator. It's impossible, right? So again, so it means that you cannot have a third factor. But obviously this reason has to be given, otherwise it's incomplete, or some other reason, yeah? So Nagesh, is this point okay? Yes, so because see, p1 minus 1 has to be even, right? Right, and p2 minus 1 also has to be even. So you get 4 as a factor from p1 minus 1 and p2 minus 1, at least 4 as a factor, right? But the numerator doesn't have a 4. It cannot have. Yes, and the even factor, so it's impossible. Slightly different reason came, but I gave this reason because see, you may, so first, but when you do more problems, you have to think and do on your own. Yeah, this is just, yeah. So fortunately, our, yes, please, any question? So see, that is in that statement only, because alpha 2 can be 0, right? Yes, you can say that separately, but it's there in that. But alpha 1 cannot be 0, has to be set. So this is again incomplete, right? Alpha 1 cannot be 0 because 2 has to be there. Okay, so that's right. So you have to do this kind of reasoning. So just reasoning on your own and then, yeah. Nice. So we have found all numbers where phi and divides n. Yeah. So earlier I had a, so what I had was a, I guess that this is the 2 has to be there, but I had this thing that maybe, so p1 minus, so if like pk minus 1 is there, so if pk is a prime, then pk minus 1 is a factor, and maybe somehow I assume it has to be prime. But then if that is there, then similar, by similar reason, pk minus 2 has to be there, and so on. And so I thought that 2 has to be there. That's what I first thought when I asked the question. But obviously that reasoning is not completely correct, but the conclusion was correct, and we got a correct reasoning. Good. So that is what we have to do. Right. And without this formula may have been difficult. I don't know, right? Without knowing this formula, may append. Okay. All right. Yes. 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 Right, because 2 has to be a prime factor, and then yeah, because first, yeah, because this second case cannot arise, right? You cannot have 3 prime factors, right? And so that's what we showed. You cannot have 3 prime factors by this even reasoning, this valuation of 2, the weight of 2 in the denominator and the weight of 2 in the numerator. By comparing this simpler thing, we found an obstruction. And so then you have only 2 prime factors, and then that reasoning they've already done. Yeah. A very interesting topic that comes out of this, which is slightly combinatorial in nature, and it's also part of things, at least the simple things in it are there, I think, is, I mean, proving things about phi n without using the formula. Okay, that's another interesting thing. And in this, I will not do a discussion now, but I can ask some questions that you guys can think about. Yeah. So, and they are very relevant questions. To begin with, they are simple and relevant, but their variations are there, which are difficult. Proving facts, and there is a lot of merit to this, because I mean, you can have a similar kind of function, right? That you could have like a sum of divisors, sum of product of the divisors, sum of squares of the divisors, number of divisors. There's so many arithmetic, these are called arithmetic functions. And not for all of them, you may find a good formula. But the reasoning you do without the formula, you can use it there. But just without all this also, you just interesting to just do. I find it interesting. Yeah. So proving facts about phi n, because with the formula, I suppose the facts which I'm, at least what I know, what I can ask, will be very easy. About phi n, so maybe I can ask some number theorists to sometime take a class, not a class, just a discussion. Yeah, sometimes they can tell you much more. I know some friends, so maybe they can. Yeah, but whether they can put it in elementary language, that's the thing. If they cannot, then there is no point, right? Yeah. Proving facts about phi n um, without the formula. Yeah, I changed the color. Right? What are some facts? And you would have already observed these things, is that phi n is always even, other than 2, obviously, is always. So I want you to find a reason for this. Okay, very interesting reasons come. This is simple, but is even. And the second is, I mean, this fact itself, that this splits, right? But this is going to be a little, I mean, yeah, little, if you want, you can try this, but you should think about it. If you, yeah, it's elementary. So this thing, if obviously, if and only, but whatever, if this, that's the important part here. I mean, this explaining that this thing happens just by reasoning is very wonderful. I think wonderful reasonings are there. Okay, so you can try to think about this. Okay. That when you take 2 numbers which are co-prime and you multiply them, and then you are asking what numbers are co-prime to n1 and n2. Right, because co-prime to n1 n2 just means has to be co-prime to n1 and co-prime to n2. I mean, it is a if and only if thing, right? Right, and so using that, can you like say that, okay, I pick some number here, can I match it with something from this? Right, so what I'm trying to say is this some kind of a matching thing you can try, is that, see, this number is not going to help you because we are not trying to use the formula. We're trying to not use the formula. You have to consider this collection, this abstractly. You don't know the collection. This collection of numbers which are co-prime to n1, n2. right? So I don't know. These things will be there, and n1, n2 minus 1 will certainly be there. This collection on this side. And on this side, you're taking these pairs of numbers, right? What kind of pairs will be there? For example, 1 comma and 1 minus 1. Well, to begin with 1 comma 1. Pairs meaning what? One number, in that set, right? One number less than n1 coprime to n1 and one number less than n2 coprime to n2, and you pair them, right? Because that's how you'll get the product, right? That's the way to get the product, or that size, that number, which is the product. And then you take one, I mean, there'll be other things, obviously, dot, 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 right? You see, so you will have something like n1 minus 1, n2, this thing, and like this. And you try to match them somehow. It's like the Chinese remainder theorem kind of thing. Just find a scheme to match them. If you can, that will be wonderful. Right? Okay, you can play around with examples. You should play around with examples and try to match them, right? So you take a number, break it up, and then look at the two things which you have and try to see, can you find a matching, and then can you extend it in general? Then you'll have a bijective proof. Yeah. Very, very important also, other than just being nice. Why? No, always multiples of 3 and 2. No. Why? I mean, they could have large prime factors, right? They could have large other prime factors. Why 25? Or are you trying to say something else? So maybe you're thinking from the formula, but then also you see it doesn't. It may not. I mean, it doesn't need to have 2 or 3 as prime factors, right? So yeah, a 7 can be a factor. Yeah? A 7 square, whatever. But you have to still think. Yeah, this is a interesting question, right? Okay. So these are the things. So we have collected some things, and also obviously we saw that a to the phi n, that thing, that big thing is there. Yeah. Okay. So now I would like to ask, so you guys would have tried some examples and such things, right? So any examples you would like to ask, you would like to share or ask, which you have tried? I think I also gave some question. I don't remember. You have to tell me. Because yeah, otherwise then I'll stop here. But let's ask some, let's see, you should have tried some questions, because we just Google Fermat's little theorem, we'll get some simple questions, right? Find the remainder when dot, 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 that happens. Or even from challenges and thrills, right? Please ask. No questions. No one has tried or what? Oh, you got everything. That is also good. Then you can share one example, right? Someone can just share one example and we can just try to see what is there. Then you have to try, right? If you're not trying, then you should try. Yeah? Otherwise, then I have to send problem sets, right? Then, but that will become like class, like it's a class, but it becomes more and more. You should try, just yeah. Obviously, I will also make tests and all, but you should just try to. Yeah, I'd also ask some questions. So if you want to ask something in that, no, okay. Okay, then I will just end. I'll end this, right? Okay, so maybe one question that I can ask. So there was just homework, maybe. There was this thing which we had done, right? That when A is, this is just homework. When A is congruent to B mod N, yeah, that implies that A to the K is congruent to B to the K mod N. Did we prove this? Yes, yeah, we proved it, right? Now I want you guys to show for homework And just a straightforward thing from here is that P of A is congruent to P of B mod n. Yeah. And what is P of A? Well, P of X is just a polynomial. Now, don't worry, just a polynomial expression that you know from your algebra. If that's all you know, then that's good enough for this, right? It's something like, just take some number and some, maybe just some x cube or whatever, right? X cube 5x square x minus 1. And then just put A in that and you put B in that, then they become numbers, and yeah, compare. So from this thing, it's easy, and just do this, prove this. Any polynomial it will work, but once you prove it for some, you depends on your level of comfort. You do it for cubic or whatever, some specific ones, or yeah. But this is something that we have proven in an interesting way, right? We didn't really need any factorization or any some result, right? We just proved it, right? Interestingly, it just came. And from there, I want you to try this. Okay. Well, Nagesh, you know that we also did this in the induction class, right? But it in fact just follows from this. So that time I didn't mention it because it would have been different, but you can see. And so these congruences are very powerful, and this is what is kind of coming from there. Okay, this is one thing. Any questions? Yes. No? Okay. So this is the one thing, and the other thing is we have already seen this. So you guys should look things, and you will find these things, these kind of questions, many of these. But I don't know if you have seen. Don't know if you do it. You guys have to do it. Okay. I'm not forcing, but in the sense that whenever, sometimes you might feel like, and that time you just do it. Yeah. And then obviously it becomes a routine and so on. See what I want to, so this is something that you know already, right? The known thing. Right. So I will erase that. What I'm asking is try to show, or try to, maybe this is a question. Okay, maybe you can try it for numbers if you want. I want you to think and show. So again, you can try it for numbers if you want, but in general, I'm asking, or take a specific prime and numbers and so on. Is that this is simply this. Obviously, these are not equal, but what I mean is when you take the remainder with P. And you would have certainly seen this. We just Google Fermat's theorem. This is one of the forms of it. Yeah. So you can try this also. Simple questions. Yeah. Please try out other things. Yeah, you would have other books and this and that. Just explore. Yeah. Okay. So then we'll stop. Yeah, it's time. Yes. So I mean, what I want to say is that if A is congruent to B mod n, then this is true, right? Let's just take, let me just say a small example. So for example, let's say that 9 is congruent to 3 mod 6, right? Then I want you to show that 9 cube plus 5 times 9 square plus 9 minus 1. This is P of 9. You agree? For our polynomial. Right, that's a polynomial. You have substituted this, at a point. Right, a general thing at a point is substituted this P of 9. I want you to show that this is congruent. Obviously, this you could just check because they're numbers, but is congruent to, leaves the same remainder, mod 6. This is P of 3. So this is the kind of thing I wanted to show. Then you see it's almost something that we have done, because you know that 9 cube and 3 cube is congruent, and you know that 9 square and 3 square is congruent from that thing, initial thing. And you can multiply 5, you can then add them almost. But is the question clear? Because regardless of everything, this is a very interesting, very interesting thing, important thing. And later on, maybe you can try to show that you can take the derivative on both sides when you learn the derivative. and so on. Like when you learn a new operation, just go and check if you can do if they are invariant under congruence, if you can apply it on two sides of congruence. Okay. All right, so then I'll stop.